Okay, perfect timing. I got these guys working on windows behind me and it's very loud. So I'll try to be focused here. We have the very great pleasure of having Bill Vass, Vice President of Technology at Amazon Web Services. I need to tell you, Bill and I have known each other since we were like 14 years old, starting out in middle school. So we're old college buddies. And Bill has had a very distinguished career working for a variety of places, worked directly for the Secretary of Defense in the Office of the Chief Information Officer for DoD. Then he was the CIO for Sun Microsystems, and then they promoted him to President and Chief Operating Officer of Sun Microsystems Federal, where he was making all kinds of things happen before, I guess, that got purchased. And so he moved on to be the CEO of Liquid Robotics, and he did all kinds of cloud-based solutions there with autonomous robots and different things for all kinds of applications. You can see his bio there. And then he moved on to Amazon Web Services, and we've kept in touch for, I guess, heading into 50 years, Bill.
Yeah.
That's hard to believe.
It's hard to believe. Yeah.
I don't feel that old, but anyway, we're thrilled to have Bill talk to us about the really cool stuff he's doing at Amazon Web Services. And I got to tell you, from a personal note, my friend Bill here has been probably the most innovative guy I've ever run across in my whole career. He's always been on the cutting edge. Even when we were in college, he was pushing the envelope on technology. So I think you're going to hear from somebody who's at the cutting edge. So I'll turn it over to you, Bill.
Great. Thanks, Glenn. And thanks for having the opportunity to let me talk to all of you. Our team at AWS runs about 42 services. We'll be talking about just a subset of those services. We won't cover, obviously, all 42 today. Glenn asked me to talk a little bit about IoT and edge processing, robotics, autonomous systems, digital twin, and where we're going with quantum computing. So those are 2 of our 42 services, actually 3 of them. So there's a lot more going on out there we can talk to. So what I'm going to do is go ahead and share my screen. And once I get my slides up, if someone will just confirm that you can see them, and that way I'll know that that they're up and running. So are you guys able to see my screen now?
Not yet.
How about now?
Nope.
Let's try it again. How about there?
Yes.
All right. Let me try to go to slideshow. And then you can confirm that you still see it, because that doesn't always work. All right. You guys see it?
Yep, perfect.
All right, excellent. Well, I'll get started then. So we'll be talking about how we're sort of extending the cloud to the edge. And we'll be talking about robotics to quantum computing and some of the things that are going on there. I think if you're into industrial engineering, a lot of industrial automation we'll talk about, and also our digital twin and our IoT platforms, the things that we're doing there. So we'll talk about what the edge is and why people go there. And the reason people are moving to the edge is, as you all know, so we have 27 regions at AWS that are spread out geographically. Each of them have 3 or more buildings in the regions. We always replicate. As Glenn may know, I do everything in 3. So every region has 3 buildings with 3 segments in it, and at least 3 buildings that are 10 to 60 kilometers away from each other. Some of them have 100 or more buildings. So some of them can be quite large. At AWS today, we deploy the equivalent of 1 Fortune 500 entire IT environment per day. So imagine, if you can imagine, all of the servers, routers, and switches at General Motors, that's how much we do in a day. And then we do that again the next day. So there's a lot that happens in the cloud. But there's also a need to push the cloud to the edge. And that's what we'll talk a little bit about and why we would do that. It generally has to do with latency. sort of the law of physics that you can't overcome. I can't make things run faster than the speed of light. The other issue is intermittent networking. So a lot of our customers run in rugged environments like oil companies or the military, and automotive manufacturers and things like that. That's pretty important. There's actually a lot of large decentralized data out there. So for example, on a seismic vessel that's doing oil and gas exploration, it's collecting about 8 terabytes a minute of data, and you can't really transmit that much over to the cloud. So you have to sort of locally process it and those kinds of things. And so it's about reduced latency, increased reliability, local processing. But the other big thing is our customers really want one environment that they can manage and deploy everywhere at the edge and in the cloud for consistency. And so, there are a tremendous number of devices out there connected to us today. At Amazon, we manage about 8.8 trillion records a day coming in from these devices. There's around 680, almost 700 million devices connected to us that are customer devices, another 250 million that are Amazon devices. So all of the Alexas out there and things like that connect in through this IoT framework. And we have to be able to manage it, and customers really want to make sense of their fleets and make sense of what's going on out there. And more things are getting connected every day. And of course, security is a really big deal in this space as well, because you're dealing with physical environments. And I'll show you examples of digital twins and full-scale infrastructures a little bit later in the presentation. It's really important to note, as I mentioned, the other thing is we have a lot of this redundant networking everywhere. In addition to that, at our data center regions now, we have what's called ground station, which is satellite dishes that allow you to transmit the data directly from satellite right into region. And so in addition to the fiber channels that are running everywhere, we have the largest fiber farm on Earth right now at AWS. We exceeded Google a couple of years ago. So it's a pretty big amount of deployments everywhere. And I'll talk a little bit about that and how those are set up. There's a broad range of devices that we can support out there, and a lot of different type of IoT devices out there, and a lot of different services that you have on those devices. And the devices vary a lot based on how much processing power they have. I often say how smart they are. The more processing power you have, the more local processing you can do. A lot of devices today, you can push machine learning models right down onto the edge and do filters sort of in real time. But it's really important to develop this sort of a single programming model for everywhere. So what we focused on a lot is we a little while ago, I guess it was about 6 years ago now when we joined AWS, we started this thing called Lambda or function-based programming, where you basically write functions directly on the cloud. And so you don't think about operating systems or databases or storage or any of those things. You can write your function directly on the cloud. And it's sort of a very advanced serverless type of programming. And so your main routine is something called step functions that you're just managing state, and then you're calling these. Now, the nice thing about them is you can write code really fast. You can scale infinitely with it. But what our customers wanted to do is run those functions on devices out on the edge, on their robots and smart devices and vehicles and things like that. And then we've extended that a function-based environment to be a serverless container-based environment. Well, so if your device can handle a container, you can run containers on there. And a lot of times we put scalar vector models on those and push them to the edge. So there's a lot of machine learning that happens at the edge on your Alexa device, or a lot of cameras out there will do, say, scene change detection and things like that. In industrial spaces, there's a lot of anomaly detection that occurs at the edge. So, for example, you don't really need a thermostat that measures the temperature every 30th of a second to send up its 72 degrees every 30th of a second continuously. You want it to just wait till it changes, or if it sees something anomalous, for example. And that would be a good example of that. So if you take a look at this portfolio out there, at the very hairy edge, we have FreeRTOS. So that is our both operating system and platform access environment. So those are probably the most common used for microcontrollers out there. So those are devices that are so small that they can't run an operating system. So FreeRTOS sort of acts as the bare metal operating environment along with the application execution environment. If you get a little bit smarter on the device, you have an operating system like Yocto or even at Windows or whatever you'd like. Then IoT Greengrass can run there. Greengrass provides the ability to deploy containers, run local machine learning models, deploy Lambda functions. It has a thing called Stream Manager that allows you to move between different types of communications and discover different radios on the device. So you might have a drone that's got, say, Iridium, 5G, 4G, 3G, Wi-Fi on the device, and it can move from one to the other if you program it to do that. And it also has Secrets Manager, which is really important for doing secure connectivity and managing that. And then we have SageMaker Neo. So SageMaker is a machine learning model system that we have that lets you build machine learning models in the cloud and push them to the edge for doing some of those filtering things I discussed. As you sort of move up to more sophisticated devices yet, we have our storage gateway product, which runs locally for doing high performance local storage. We have digital twin capability for whole factory level or whole building level things. Kinesis Video is a really popular product we have that will ingest any LiDAR, radar, or video information very simply into the cloud and process it. So you can use it for photogrammetry, pull all sorts of information off. It happens to also run on RoboMaker. So RoboMaker is what we use to build and deploy robotics and autonomous systems. So that's the software stack. It does the simulation, it does the deployment, it does the management of your fleets of autonomous systems and robotics. We recently released sort of a thin client Alexa, so you can build voice services into just a light switch, for example, and the processing happens back in the cloud. And then we have our Snowball products, which I'll talk a little bit about. These are our ruggedized edge shippable devices. So there's a larger one, like the Snowball Edge Compute Optimized. It's got 5,300 GPUs and 52 x86 cores, 100 gig networking. It weighs under 50 pounds. It'll handle 200 G impacts. It will operate at minus 53 degrees plus 140 degrees. It's got an e-ink label on it, so it ships itself. It's rack mountable. It's being under 50 pounds, you can check it as luggage or any common carrier can have it. And we have our smaller devices like our snow cone device, which is a smaller Snowball. This is designed to operate in a drone, for example, but it's got the same sort of e-ink label on it, so you can ship it automatically. And it's nice. This is $6 to use, and the big powerful one is $30 to use. So they're pretty cheap to use. You sort of use them on demand for processing things at the edge. We also have CloudFront, which is our CDN system, and our POPs, and you can run Lambda functions there as well. We have Wavelength, which we're rolling out these outposts in our all of the 5G sites in the world, and Outposts, which are local extensions to the cloud that can run locally there. And then we have local zones that run in a region, and then regions that are sort of those 3 availability zones that I talked about, that we do everything in 3s there. And so that gives that redundancy. So it allows us to stripe the data across 3 geographical locations. Our goal here is to provide sort of end-to-end security, end-to-end development environments, end-to-end deployment, end-to-end management, and let you sort of set your latency requirements in place. So for example, you can't run a Lambda and container function on FreeRTOS. I wish you could, but you can't. That's not powerful enough to do it. But starting with Greengrass, going all the way back to the cloud, you can use the same Lambda function or same container, and you can also cascade them across this entire end-to-end piece here, and you can deploy them and manage them. So those are all really important pieces of the infrastructure. And this just sort of gives you an idea what you'll see out there. We have 27 regions, 77 availability zones, 216 POPs, 205 edge locations. And you can connect locally or to POPs or straight to the cloud, depending upon what environment you're in. And our goal is to make it sort of seamless for you to operate in these places. So these are the Snow family devices that I talked a little bit about. You can see them there, customers using them all over the place. They're very popular in the military, very popular in oil and gas sites and things like that. That's what the device looks like. The reason the device is gray, that's called cool gray. It's actually infrared reflective, so you can leave it out in the sun and it doesn't get hot. And I think that's important for it. It runs on unconditioned power. They can be clustered. It passed the DoD barge test, which is where they blow up 83 pounds of plastic explosive 20 feet from the device 6 times in a row. There's a YouTube on that if you want to go see what it's like to go through that. It's about 66 G of force there. And they're rated for airdropping. We do have customers that airdrop them as well. You do need a parachute. You can't airdrop it without a parachute, but it does have to have a parachute. But you can imagine these are used in a lot of places, but they allow you to run EC2, S3, a lot of our stuff that acts as an IoT hub and things like that locally in these environments where the network is either intermittent or the environment is poor. And I think that those are important for all these different locations. They're heavily used in the movie industry for doing movie shoots. That's how a lot of the movies you see are shot in the field. They're used for drone operations. They're used on seismic vessels and things like that. We have customers like NGA that deploys them in large fleets. They're also rack mountable there. There's actually an e-ink label on the top. You see of it there, and then a touch screen on the front for QC and other things like that. But it's been a pretty cool product. A lot of customers using it out there. But a number of customers came and said, well, that's great, but I don't need the ruggedization, but I do need the local low latency processing. So from that, we developed a thing called Outpost, which is an extension of the AWS cloud locally. So it allows, full AWS services running locally, connected back into the cloud. Some services can run on the device. Some services still run back in the cloud. On the Snowball, everything runs on the device. But it has our Nitro card capability, which you can read a lot about. One of the things about AWS is everything's multi-encrypted, and our administrators can't access any running instances in the cloud. And we're abstracted from the instance through a thing called a Nitro card that handles layered encryption, authentication, and also administration without us giving access to our administrators to a customer instance running on the device. And it allows us to basically remotely patch and update these when they're in people's data centers. But you can run your low latency processing right here on the Outpost, and it can be right next to your factory floor or even on your factory floor. You can have Snowballs out in rough environment areas running processing there. And then of course you can run on the devices as well. And the idea here, again, with the same CloudFormation template, you can deploy across all of them. You can manage them all centrally. So how far can the edge reach? There's a lot of different distinct types of robots, for example, that use RoboMaker out there, drones, robotic arms, ground mobility systems. So RoboMaker is built on ROS 2, if you're familiar with that. It's an industrial version of ROS that we've come out with with the open source community. We're the #1 contributor to ROS 2. We put the DDS high performance messaging system in there and worked on upping the security significantly. All of our systems have to run what's called authority to operate top secret compartmented information, because we run the intelligence agency's clouds, and those are life critical systems that run at the TS-SCI level 6+. And we do the same exact security with our commercial products as well. There isn't any difference in the code or the hardware that runs in the intelligence agencies versus what runs on our commercial cloud. All of them meet that high level of security. So RoboMaker allows you to develop your robot, and then you can build simulations, which are nice 3D simulations with physics and everything. And you can see there on the left is a robot that's designed to do a decontamination of COVID using infrared, and goes around and does that. Wear sunglasses when you look at it. Anyway, if it detects a person, it turns itself off. And then other robots that are built for healthcare simulations. And then on the right, you can see where we're working for fulfillment centers, which I'll show you a little bit more there. But RoboMaker allows you to do the development, do large scale simulation in parallel, and then do deployment out to the actual devices and then manage them in fleets. And also manage the machine learning locally for those. And so this is a 3D world generation. Our team also does all of the movie studio high performance computing for rendering and gaming. So you can see how this begins to look a lot like a gamified interface, and you'll see more of that as I go on. WorldForge is something, if you've ever built one of these 3D environments, you have to hire an artist and go out and build an environment. It's a lot of work to do. WorldForge, we released it recently, and what it does is it generates synthetic 3D environments for you. So you give it a set of rules, like I want a house with so many rooms in it and so many doors, and I want these surfaces and this furniture, and then it'll randomly create houses for you to test your vacuum cleaner robot in. We started with houses, and then we'll do office buildings is coming next, and then after that we'll do outdoor spaces. So if you're familiar with, there's a great video game called No Man's Sky, which gives you an infinite universe that's synthetically generated. It's sort of the same idea. Is you can synthetically generate tens of thousands of different houses and then test your robot out in it doing machine learning, or thousands of different factory floors or thousands of different buildings. And in RoboMaker, you can actually sit and watch the code running line by line as it goes through, and then you can watch what happens with your robot. And if it bumps into something that sets off a CloudWatch alarm, you can go watch it, change the code, deploy it again, and it will retest in that environment. And then once you have tested in all these synthetic houses and you're happy with it, you can deploy it out to your real robotic fleet 10% per day with automatic rollback. So you can put 10% out with new code on. If they have any issues, it'll roll back automatically. If it doesn't after a day, then the next 10%, the next 10%, the next 10%, right? So we've got a lot of experience doing this ourselves. So we have to build all these services for ourselves. In fact, AWS came from things we had to build for ourselves that we've opened up to external products. So we have 175 fulfillment centers all over the world today. 50 of them are robotic. We have about 250,000 robots that we manage in our fleet, and about 200 million Alexa devices enabled out there today. So there's a lot that goes on that we have to manage in here. So what I'm about to show you is one of our robotic fulfillment centers, and hopefully the music won't play. Let's see if we can do this. I will mute it because otherwise, there we go. All right. So on the left side is where product comes in. On the right side is where product goes out. And we actually move the shelves to the pickers. Underneath the shelves, they all start about 12, I think maybe 16 inches off the ground, and the robots can move freely underneath all the shelves, avoiding the legs. They pick the shelves up and bring them. So they're working in swarming algorithms here. So you'll see they'll just avoid hitting each other here. And so product comes in one side, goes out the other, and you see how fast some of them are moving there, and then they just stop and just barely avoid hitting each other. It brings the product to the pickers. The pickers are a combination of people and robots. They're on the edge. So when you order something, and you can try this out, we have an SLA that within 20 minutes in our fulfillment center, if you ordered it from Fulfillment by Amazon, within 20 minutes of you ordering it, it is in a box in a truck, basically. And this is how we do it. We don't have people running up and down aisles or anything like that. The robots do all the running, and the product is brought to the person. And it's interesting. This was designed using simulation, because if a human designed this, you probably would have put everything in the Dewey Decimal System and been running up and down the aisles grabbing books, so to speak, or grabbing products. That's actually the worst and slowest way you could do it. You want the products to be as random as possible. The more random they are, the more picking you can do in parallel, right? Because you're spreading the load out. The more sequential it is, the slower and more horrible you are. In addition to that, you'll notice that when we first did the design for this, human designers put the pickers in the middle with aisles of robots between. And through our simulation systems, we learned that that was a bad idea. That it's better to have all the pickers on the edge. And yes, the robots can detect people. People don't usually go in this space. It's fully autonomous. If someone walks in here, an alarm goes off and my pager goes off. So I don't like people to do that. But that's how things will happen for our robotics teams. This all runs basically fully autonomous within here. Obviously, there's people manage it. There's people manage the system. This is managed on the cloud, and some of the processing is done on the edge as well. So the edge is at home. If you've got an iRobot doing vacuuming at your house, it's running RoboMaker. The edge is on the road in autonomous cars like Mobileye and other things like that. The edge is on a boat out in the middle of the ocean running snowballs and things like that. And the edge is in IoT devices with Philips, for example, in hospitals. And so those are the places we sort of look at the edge. But the edge goes further than that. This is the Mars rover on RoboMaker that's on its way to Mars right now. And so in this simulation here, we had to calculate the angle of repose for the fine dust on Mars so the rover could be tested out in all different ways and all different terrains with it navigating, because it needs to navigate autonomously. So in this case, you've got logic running on the robot, because as you know, between here and Mars is about a 20-minute round trip. You can't do that processing on the cloud, but we did a lot of training on the cloud. So it's very cool to see that. That's the open source Mars rover. You can actually download the code and try it out yourself, and even buy an open source version that you can assemble. So it's pretty cool. So this sort of brings us to this idea of digital twin. Remember, I said our team has gaming services along with video production and things like that. You're starting to see this sort of integration of the gamified interface with industrial and digital twin physics models as well. And so we'll be talking about, this is a example here is a liquid natural gas plant that we'll talk about here. So one of our customers is a customer called Woodside Energy. They're an LNG producer out of Australia. This is a digital twin of their plant. They have about 250,000 IoT sensors per plant. They've automated robotics for doing inspection, and also the robot can interact with things. They have drones that fly around the plant with methane sensors on them. They used our Kinesis video product to put cheap video cameras everywhere and do machine learning on the video cameras, doing machine learning on the anomaly detection and maintenance capabilities for their IoT data. They're doing edge computing right here and proactive maintenance. So what you're about to see is they used a drone and a robot to create a 3D photogrammetry scan of the entire plant. They do that every month. Along with importing the CAD CAM, and you're about to see the user interface they use to manage the plant. So here is the CAD CAM. So, well, this is actually the photogrammetry. And as they come in here, you'll start to see the IoT data pop up, and you can see the robot doing its inspection there on the lower right-hand side. And you can see that's the actual compressor speeds and vibration and temperature popping up there in real time. As the manager here switches over to the CAD CAM view, they overlay that with the real-time video. So you can see the real-time video. And if you see that little 90-degree pipe there right in the center, you're about to see the robot go do an inspection on that. But you can see here as the video pops up, they can zoom in on the oil level there. That's done with a machine learning algorithm with a camera to calculate 86% because there is an oil level sensor on the compressor. And you can see they can zoom in and take a look at what's really going on in real time while they're managing this plant remotely. They can see trends, and you can see it inspecting that little pipe there. That's where the robot is right now. Now the machine learning model opened a valve about 11 minutes ago here. So they're going to send the robot over with its thermal camera to make sure there aren't any thermal issues. And now the robot's looking at that same area with its thermal cameras and doing a thermal inspection. And you can see where it changed the valve position there, and it's 100% open 11 minutes ago right now. And so the operator is happy with this. You can see the LiDAR coming in real time. That's the RoboMaker console down there. He's going to switch to the LiDAR view, fly back through the plant. Those are people that didn't stand still long enough to get scanned. And then you can sort of see this idea where they stop and take a look at the compressors and the compressor data to check that out. And you can see the robot going on and doing its inspection with its cameras and its LiDAR and things like that. So along with the real-time cameras there that are coming in through Kinesis video. So this gives you an idea of the sort of gamified interface you expect in these digital twins. There are physics models behind these. They can do models for different temperatures, different mixtures of oil. They can do, tests of fire suppression, a whole bunch of things that operate in this environment. So that's a lot about what we're doing today on the digital twin and robotics environment. Now we're going to switch gears and talk about the future. Which is what we're working on in quantum computing. So for those of you who are not familiar with quantum computers, that's not a quantum computer. That's what they always show as pictures for quantum computers. That's the refrigerator. All of those curly cubes and things like that are piping and lines going down to the chip that sits way at the bottom of that picture there. Quantum computers, you're doing basically measuring phase and vibration of particles. So you want to get them as cold as possible, generally speaking, to remove vibration because that messes up your computing. If you take a look here there's different types of quantum computers that we run today. There's ones based on electrons, which are probably the most common ones. They're often called cryogenic electromagnetic machines. And so they use electrons tunneling at cryogenic temperatures to act. The electrons all act as a single particle in that case to form the qubit. There are ions, and I particularly like this one. This is the ion Q machine because you can actually see the ions glowing blue with the naked eye. Now that little zoom up there that's not really what it looks like. It's that slit in the chip there is where you can look in and see those blue ions. So the ions are charged particles, as you know, and they suspend them in a magnetic field. And they use, in this case, instead of cryogenics to cool they use lasers. So they use what's called sympathetic cooling. So you're basically, if you can imagine, like, heat is just vibration. A child on a swing, you wouldn't walk up and just stop them from moving. You would push slowly in a, reducing sine wave till they come to a stop. You do the same thing with a laser. And so you use lasers with an ion trap machine to set the entanglement and set your circuits up and to measure them and to cool them. There's also machines that we have coming out that are photonics based, and we're using photons, and there's machines coming that use just different types of atoms. But in all cases, your qubits are basically a particle. Now, you build your circuits through entanglement, as Einstein called it, spooky action at a distance. No one really actually knows what allows entanglement to occur. We understand quite well what it does. The way I like to think of it is we live in multidimensional space, and you're entangling these two particles, creating a chemical bond in a dimension that we can't measure. That's the way I like to think about it. I don't know that that's really the way it works, though. You guys, Glenn should be able to answer that question. You can ask him how entanglement works. Anyway, so you're particle physicist. You can have long philosophical discussions about that, but we do know that it does work, and that's how we build our circuits and perform logic. So the more qubits you have and the more levels of entanglement you have, the more complicated problem you can solve. The control plane for them are usually microwaves or lasers that you're using. These are analog machines, not digital machines, and that's important to understand. And you're measuring spin and direction on these qubits. And so remember that curly cube thing. Basically, this would be like a chip that sits at the bottom of that curly cube thing. Now, the ion trap machines don't have a curly cube thing because they are not cryogenically cooled. They're cooled with lasers and synthetic cooling. They actually do cool it with nitrogen just because it runs in a vacuum, and that slows particles down. You can never get a perfect vacuum. so that they don't interfere with the ions there. But it's actually pretty cool. The ions move back and forth. I don't know if you guys remember typewriters. Some of you, I'm sure most of you do actually, but my kids don't. But the ions move back and forth in the magnetic field with a carriage. There's 3 lasers that point at each one. The lasers are stationary, and they use the magnetic field to move the ions back and forth to entangle them, set them, and cool them. So it's a pretty neat piece of kit. So basically, how does it work? You have an input device. We use Jupyter notebooks, if you're familiar with those, for setting up your circuits. You define your circuit. You set the entanglement in place. You do your computation. You measure the output, and you get your output. So it's pretty simple. So physically, what does that look like? So you have a web browser with a Jupyter notebook running on the cloud that you can access. You write your code in Python. You set up your circuit. That circuit gets sent through an encrypted channel down to either a snowball or a outpost sitting in the room next to the quantum computer. The quantum computer, that machine actually controls, in the case of the machine you're looking at there, which is a cryogenic machine, it controls the microwaves that are setting the qubit at beginning state and doing the entanglement. The chip is sitting down there at the bottom of that tower there, and there's the chip you can see that's actually doing it. The qubits are doing their thing and running your circuit for you. Then you use microwaves to detect it. The output is then put back on a classical computer, as we call those, and that's connected to the cloud and goes back, and then it shows up in your Jupyter notebook. And so the thing that's interesting to me is these quantum computers actually work. You can solve real problems with them. You just can't solve problems you can't solve with a classical computer. There's also a lot of hype about quantum computers that they're going to replace classical computers. Nothing could be further from the truth. Quantum computers don't have a concept of quantum RAM yet. There are some ideas around quantum RAM. They can't do heavy I/O. They're not going to run things that require a lot of I/O. They can generate a massive amount of data, though, when you're simulating a molecule or something like that. And those are the kinds of things that they do really well. Optimizations, equations, things like that will become very hard to do, or already very hard to do on classical computers, because of, classical computers use a clock and a looping structure, and quantum computers use quantum physics. So it's a very different type of machine. So what kind of problems are our customers working on with us? Fertilizer production doesn't sound like that big a deal. You wouldn't believe how much money is spent generating ammonia. So one thing that's really interesting is if you took and you made a Hamiltonian for ammonia, and if you know anything about biology, there's some bacteria that can generate ammonia very inexpensively and quickly with very little energy. It takes us a massive amount of energy to generate ammonia, generally speaking. And we don't know how the bacteria does it. We have no idea. If we could figure it out, it would be transformational for our industries, because ammonia is a key component in a lot of manufacturing today. And also, we'll talk a little bit about ammonia and how it's used in the non-hydrocarbon world on the next slide. But ammonia synthesis is a big deal. If you took all the computers on Earth and had them run that Hamiltonian, they wouldn't figure it out if they ran for the history of the universe. So about 14 billion years of all the computers in the world working couldn't do a Hamiltonian on ammonia. Now, you can do a Hamiltonian on a water molecule today on both a quantum computer and a traditional computer. But ammonia is too complicated, and a lot of molecules become too complicated for us. And so how many qubits does it take to do ammonia? About 1,000 error-corrected qubits. How many qubits are available today? The largest quantum computer in the world is 52 qubits. That's actually not that far away, to be honest, though. Error correction gets to be a big deal on quantum computers, though. It increases exponentially as you increase the number of qubits, the errors. And errors occur on classical computers as well. You may not realize it, but alpha particles are switching bits on your iPhone and your laptop all the time. We just have ECC built into those chips to avoid that and to get control of it. So this could be a very big deal if we can get this to work, and it's one of the focal areas for us. Sustainability, obviously, carbon capture, and new types of materials that could capture carbon is a big deal. But the hydrogen economy is a big deal for us as well. So you may or may not know, Amazon has committed to switch to entirely carbon neutral by 2030. That isn't that far away. One of our big challenges is, you may have heard, we bought a lot of Rivian battery electric vehicles for our logistics, and we've bought hydrogen trucks for our logistics as well. One of the big challenges is that you don't have enough grid energy at our fulfillment centers to charge all those vehicles. And so we're looking to, we already have hydrogen running our automated forklifts at our fulfillment centers as part of our commitment to move off of fossil fuels. And we're working on having hydrogen storage and fuel cells there. In addition to that, though, we have to look at our entire supply chain. So it isn't just the trucks, it's also a huge amount of things are moved on container ships, and container ships run bunker fuel and are just absolutely environmentally horrible. So there's some prototype ships they're building where they actually have ammonia instead of the container fuel, and they use ammonia going directly into fuel cells that power the motors that run the ship. And so the ability to produce ammonia cheaply with low energy impact is another way. Ammonia is another way to transport hydrogen cheaply. And so again, this could have huge impacts on the future if we can figure this out. Much more energy efficient solar cells. The best solar cells today are gallium arsenide cells that are multicolor cells that they use on satellites. They're incredibly expensive. I used to use them on my my autonomous systems because they had to run for long periods of time. Your traditional silicon-based solar cells are about the best. I think SunPower is 22% efficient. Some of the cells they use, the more expensive cells on satellites, are almost 40%, 41% efficient. So if we could come up with a much better way using, again, a Hamiltonian simulation to harvest energy from the sun much more efficiently, that would have big transformational changes on our economy as well. Pharmaceuticals, again, drug development's a very long process. The ability to simulate and fold protein molecules is something else that we could do with a quantum computer with sufficient number of qubits. And so that's another area of focus for our customers. So, when is all this going to be possible? Again, today we have what's called noisy qubits, less than 100 qubits. As I mentioned, the most number of qubits out there is 52. Next year, we'll have hundreds of qubits available. So it's increasing quickly. In the next 0 to 10 years, we get to the point where we could have 1,000 noisy qubits, and that's when things really start to get interesting. In fact, for certain things, 100 qubits gets to be pretty interesting as well. And then in the 10 to 25 years, that's when we're really cooking with grease, and it could start solving some really big problems when we start getting error corrected qubits. Where ultimately, and you'll hear things like, well, Amazon is deploying quantum safe cryptography today, and we are. Why are we doing that? Well, you can store data for 10 years easily on things like Glacier and S3 and things like that. If you monitored all the network track of it and stored it, you'd have everyone's keys and everyone's encrypted data stored. And then when you have enough qubits to run Shor's algorithm, you could break it. And so that's the reason we recommend for transport layer to start running quantum safe cryptography today. But just to put things in perspective, we're at about 100 qubits today. Well, about 52 qubits today, 100 qubits next year. You need about 2 million qubits error corrected to break Shor's algorithm. So we are still a long way off, but things are increasing exponentially, kind of at a Moore's law rate, if you like, in the manufacturing center. So it's pretty exciting times right now. Now is actually, we believe, a good time to start writing quantum code and experimenting with it, but it won't solve your problems yet, in spite of all the hype that you're going to hear out there. So what are we doing? We launched Bracket, which is a Dirac's a quantum notation. That's where that name comes from. It is not misspelled, Glenn. That's probably the first thing he was thinking there. He knows I'm a bad speller. We didn't misspell it. Bracket is the two parts together. You can go look that up. Anyway, it was in honor of Dirac, and it's probably the only quantum service that doesn't begin with a Q. We tried to find something that didn't begin with a Q, but anyway, and then we'll talk a little bit about that in more detail. But you can go out and run a quantum circuit for a few cents right now on AWS if you want. Anybody can do it. We have our solutions lab. And so these are working closely with companies in those areas I just talked about, where quantum computing is going to be really a big deal. And you might remember the traveling salesman problem if you ever took, computer science classes. That is actually a classic, I guess, NP-hard problem. And it's the same problem we have in logistics. And there's this company that ships a bunch of stuff around. And if we could save money on optimizing logistics in real time on our delivery systems, just a 1 or 2% savings is billions of dollars for us. So it's one of the reasons Amazon's investing in quantum computing for ourselves. And then with Caltech and MIT, Stanford, Harvard, and Yale, we created the AWS Center for Quantum Computing, where we're doing a lot of detailed quantum research that I'll talk a little bit about. So what is Bracket today? So if you go on our traditional cloud, we offer multiple databases. We have databases from Oracle and Microsoft, along with open source databases and our own, like Aurora. From a chip perspective, we offer AMD and Intel and NVIDIA, but we also offer our Graviton ARM-based chips and our inference chips for machine learning. So we are all about choice, and we're the same way with quantum computing. So we have multiple vendors available on Bracket. There are 3 machines available today, right now. You can go run on these quantum computers right now as we speak. You have a Jupyter notebook where you define your circuit and the problem you're trying to solve. There's a local IDE for it, and you can also access through the Bracket console interactively and put it together. What you generally do first is you'll do a simulation of your circuit to make sure it's working right on our standard EC2. And once you're happy with it, you schedule a shot or a series of shots on 3 different quantum computers. It's a common API for all of them. One is an annealer called D-Wave. Another one is a cryogenic machine called Rigetti. And the other one is an ion trap machine that I showed you a little bit more detail on, called IonQ. There'll be more machines being added to this. Our goal is to have many choices of machines. There's innovation happening in all of these dimensions. Different machines are better for different things. The cryogenic machines set up faster and get your results faster in some ways. They're a little bit more noisy though, and they aren't coherent for as long as the ion trap machines, but they take longer to set up. The annealers are good for very specific things, but not what I would call general purpose things yet. But they're also working on gate-based additions at D-Wave. D-Wave's got a pretty advanced system and has been around for a long time doing this. So you'll run your simulation, then you'll schedule your shots. And if the machine is online, now these machines are in early days. They aren't online 24/7. Generally speaking, they're up for about 4 hours and down for an hour for manual calibration, then up again. So if it's down at the time you execute it, it'll queue up and then it'll send you a message when it's done, so you can get your output. Then what we're also working on is these hybrid algorithms where, I think I was pretty excited. In November of last year, I had 2 quantum computers and EC2 passing variables back and forth to each other, solving a problem together. And I think that's a pretty amazing thing that you can do with it. And it's fully integrated with our cloud. So you get, CloudWatch metrics just like anything else, and notifications and alarms, and you can store your stuff in an S3 bucket and use our identity systems. Everything's encrypted and securely connected to these machines. So it's a very secure way to do computing as well. So what does it look like? When you go into console, you have a choice of choosing. Again, it's the same development environment for all of them, but you can choose whichever one you want to run on. You can choose your devices, and it tells you the status. Like in this case, this was a good day. Everything's online. Everything's available now. You can see, except for Getty is next available. It gives you the time when it's next available. So they must have been calibrating at that time. You can also see the amount of error and noise in each machine when you run. You can see how many qubits. There are two D-Wave machines, a 5760 qubit machine and a 2048 qubit machine. Now, Annealer's qubits are different than gate-based qubits, and Ion Q and Rigetti are gate-based qubits. So again, don't confuse those. The interesting thing is IonQ just announced a 32 qubit machine as well, and Rigetti's working on their 52 qubit machine. We will have more machines coming online soon, so watch this space with more technologies coming online soon. Ions and photons are also used heavily in quantum networking, so that's another area to watch also. We use is a way to distribute a key material using entanglement with ions. And there's also, that's used by banking and the intelligence agencies. And there's also a way to use entangled photons to distribute key material and make sure it isn't intercepted. So some interesting things happening in those areas as well that are not directly related to quantum computing, but other areas that we're working on. So this is what a Jupyter notebook solving a basic and setting up a basic circuit is. And then down there, you can see the result coming out from it. Our goal here is to have lots of use cases, build prototypes and benchmark, and we have a whole solutions lab to work with you. And I believe we've already given your team credits to go run on Bracket. So this is what the team looks like, and you can actually see electron microscope close-in zooms of the circuits we're building down there in Caltech. So that's sort of with that. I think we're going to stop sharing and open it up to Q&A. I think I'm right about on time. I scheduled about an hour. All right. Any questions on that, or I can cover anything in AWS you're interested in?
Yeah, I had a quick question about what temperatures do the quantum computers reach?
They operate at microkelvin. So about the ion trap one runs really hot. It runs at minus 473 degrees Fahrenheit. So, but the others run much colder than that.
So are you worried about any kind of phase changes in that? Because if I remember correctly, that's going into the realm of Bose-Einstein condensates.
Yeah, we're definitely down there in a singularity kind of environment, almost at that level of temperature. The goal, though, remember, we're measuring the vibration and phase change of the particles, and so we don't want heat to interrupt the compute at all. So all of them have to operate at very, very cold temperatures. Now, the thing I like about the ion system is you're doing sympathetic cooling without all those refrigerators. Everything else has really massive refrigerators and cryogenic systems. So, and they have a cryogenic system too. I don't want to make so that there is some cryogenics there. What they do is they do a vacuum, and they're using the laser to cool the particle to stop it from vibrating. And that vacuum, if a stray molecule or stray atom bumps into it, it'll cause it to vibrate again, and that heats it up. So they actually make the vacuum cold with nitrogen so that doesn't happen. But they're not relying on the cryogenics to do the get to the microkelvin for the compute. They're using the lasers to do it.
That's literally, Bill, that's just really literally using light pressure applied at the right frequency
Yeah.
to stop the particle.
Yeah, yeah, it's just like remember that little globe thing with the vacuum that would turn that we always had. You have the black and the light. It's the same thing. It's fascinating to me. So they'll use the light pressure to get it to stop moving, and then they will initiate a photon out of it using the laser and send that photon to the other qubit they want to entangle with, and that passes the information to entangle them. And then they'll run their compute, and then when they're done, they'll use the laser to measure the frequency and vibration. So it's a 3 laser system, and they have that carriage of ions move back and forth in front of it to do that. So they're like, if they're entangled this one and this one, they'll do the work here, and then they'll cool them all down, and then they'll move over and entangle this one with this one, and then they'll go do the measuring. So with the cryogenic systems, you're using microwaves to do the entanglement, and you're steering the microwaves with a metamaterial, which is pretty fascinating as well. And the metamaterial is basically just a very fine grid of aluminum that is printed with a dopant on the chip in a fractal pattern. To make it be able to steer the microwaves. It also steers electrons when you're entangling the qubits. And so the more you can intertangle, the more you can complicated problem you can solve. The other thing with the ion trap machines that's interesting is they're working on sending those photons I mentioned over fiber to other machines. So you can entangle, in theory, more than theory, they've done this a few times in the lab. They don't have it operating yet in production, but you'd have 2 machines, and you could send a photon from this machine to this machine and entangle these 2 on 2 different machines. And so that allows you to horizontally scale, which I like a lot. My engineers don't like the ion trap machine as much, but when I was at the, are you familiar with the Jasons? You have to know about the Jasons. Okay. Yeah. So when I was working on the Jasons, I helped to fund some of that when I was at NSA. Chris Monroe is the guy who started IonQ, Dr. Monroe at the University of Maryland. We funded a lot of his research. And so I was very, very, I like the ion trap ones. It's the easiest one for me to understand. The quantum computing is it drives me crazy because no one knows how entanglement actually happens. Like I said, the best I can get out of anybody is it's a chemical bond that you form in another dimension, so you can't see it, and that's why you can move the ions anywhere you want, and they still stay bonded. You can send one to Jupiter and the other one here, and they still stay bonded. And when you measure both of them, you snap them back into our space and break that bond. That's the way.
It's all prescribed quantum states of particles.
Yeah. So you snap it into our reality, so to speak, after you measure both sides. But it's a Schrodinger's cat thing, and you can't, so it's really hard to do error correction on it because you can't measure it while you're doing the error correction, because if you measure it, you break the entanglement and then your compute doesn't work. So there's a lot of interesting stuff there. But yeah, I mean, I ended up doing quantum computing because I used to complain we weren't doing enough about it. And every time my boss would ask me, "Why don't you just do it, Bill?" I said, "I hate quantum computers. I don't want to do it." Because you know me, I like to know how everything works, and nobody knows how it works, right? Of course, my team, bunch of PhDs, much smarter than me on this. They're like, "Well, we know how it works, Bill." And then I'm like, "Okay, well, how does entanglement work?" And then they all start getting all wishy-washy and stuff. But they know how it works, as in what it does, right? It's like my wife is a very smart person. She's a PhD lawyer and all that other stuff, but when she gets in a car, she puts on the gas and she puts on the brake. She doesn't know how many cylinders it has. She doesn't know any of that other stuff. And she can very effectively drive the car. And now we have electric cars. She doesn't really have to understand that. She just knows she's got to plug it in and she can drive it, right? And she's a very smart person. She just has no interest in knowing that stuff. I have to know how all that stuff works, right? When I push the gas pedal, I got to know how it all works. And with a quantum computer, you just don't. But you can drive the car just fine, right? Whether you know how to work or not. So you can put your circuits in, you can solve problems. And I think There's been some pretty interesting stuff on correlation that we'll be releasing soon. I'm really excited about. A lot of really good work that the team has done. So I'm very proud of them and what they've been doing. But yeah, it's fascinating stuff.
I have one question about, you went over so many of the different technologies that
Yeah.
you're overseeing.
Yeah.
One of the things that we're trying to better incorporate in and I'm doing, nuclear engineering, but
Yeah.
we also have civil and environmental. One of the things is the smart cities, smart buildings, and all of that. It sounds like you've got a lot of what I would call turnkey solutions to make that happen for smart buildings and how to design smart cities that are engineered to be super energy efficient. I mean, you could really use all these IoT
Yeah.
devices pretty much out of the box, right?
Yeah. Well, you can use them out of the box. What we don't have yet from Amazon, but there's a lot of companies that built on us, is generally what we'll do at AWS is we'll build sort of the Lego blocks, right? Very detailed, good Lego blocks that let you build, you can build a pirate ship, you can build a castle, you can build whatever you want, right? And so slowly, though, we do move upscale. But we, for example, on that that refinery example, so they're saving a significant amount every month in maintenance, predicted maintenance and operating costs by doing all that IoT stuff. But we don't have the engineers that would do the process control models for that, right? They do. And so they put the process control models in. What we do is enable the hard work, what we call often undifferentiated heavy lifting, the hard work of getting the devices connected, getting it streaming, letting you deploy your machine learning models, letting you aggregate it, letting you do analytics, letting you do those things. We don't provide, for example, a compressor model. The manufacturer provides that. And then you, as a user, would integrate the IoT stream with the compressor model to determine what the maintenance requirement is. Now, we could show you how to do, for example, a machine learning model on that stream and say, oh, this is anomalous, right? You need to look at it, right? That we could do, those kinds of things. So generally, we're working with someone like a Siemens to do a smart building, right? Or others, right? Coney, who does elevators and things like that. Carrier, for example. We just announced a big thing with Carrier. We do with Volkswagen. We're automating all of their manufacturing and logistics using our IoT, working in partnership with them. But we're not the experts on Volkswagen logistics, right? There's a lot of business rules involved in that. We can say, this connects to this, and we're getting a secure connection here, and it says 26. I don't know what 26 is, but that's what it's telling me, right? It's the the Volkswagen engineer that understands that 26 is actually temperature, and that's good, right? It's in Celsius, and that's good. Or 26 is too hot for this manufacturing that they're doing, or whatever it happens to be. And then people like Woodside do these huge physical models. Now, what we're also working on is city size simulations, where we do things like with our gaming engine and other stuff like that, which I could run a short YouTube and show you the gaming engine if you want, and see what that looks like, so you get some idea of what we're doing on the rendering side for all these things. But we also pull that into our movie systems, but also our full scale physical simulations, which will link into the digital twins to do city size simulations.
That's really cool. I was thinking that you're talking about all these hydrogen powered vehicles and ammonia powered vehicles, but you got to produce that with either hydrocarbons, which is a bad way to do it, or I would say nuclear power would be the way to go.
That would be a logical thing, but that doesn't mean that that's what we'll do.
I was going to ask you. I can hook you up with INL, because the new director at INL is a good friend of mine. So
Bill Gates has some really good investments there, actually, and so I think there's a lot to be said for that. Today we're doing it. We have a lot of hydroelectric up here. And so the hydrogen and stuff's being generated with hydroelectric. There's a company in Norway that's using hydroelectric for it. And the other area is wind and solar. So we've been sort of offsetting all of our data center use with wind, solar, and hydroelectric. and feeding it into the same grid. Now you can argue whether the electron that came from the wind farm is actually being used in our data center or not, right? Or in our hydrogen production plant or not, you know, but we're feeding the equal amount of electrons into the same grid we're pulling electrons from, but there's also usually natural gas plants feeding into that grid as well. And I can't tell, I guess that there's no way to tag electrons and say, oh, I'm not taking that electron, it was generated, or that, but our goal is to offset it all every place we can. I'm not, scientifically speaking, a nuclear plant makes a lot of sense in a lot of ways, properly managed and run. But after what happened in Japan, it's really hard for people to see that,
Well, hopefully it'll get better. We're going to need some of those smart systems to monitor some of these nuclear plants, especially these small modular reactors. So they're going to be kind of set-asides that are going to run by themselves autonomously. I can see a lot of uses of the IoT devices that you're talking about in monitoring the state of health of that plant. And also building construction.
Yeah, but that's also why we spend so much time on security, right? So we run the intelligence agencies clouds and the DoD clouds as well, and those are huge targets. And so we run, for example, like the snowballs, we run with the data that gets stored on this. It is encrypted 3 times with 3 different key management systems and 3 different encryption algorithms.
Is that all internal? It all runs autonomously inside. So when you get your data, you're not having to worry about how the encryption algorithm worked.
Right. But actually what happens is when you provision the snow cone, what'll happen is you can say, I want these EC2 instances to run on it. And I want this data. Is this e-ink address will change to your address, and it'll make an API call to UPS or whoever you've chosen as a carrier. We'll throw it on our loading dock. It'll ship to you. But when you generated the manifest, you used your cloud key, which isn't on the device. So there are 2 TPMs on the device with 2 keys, and the cloud key that makes your 3rd. And so even if someone were to get through the TPMs, there are 3 layers of anti-tamper on this and 2 TPMs, they still couldn't decrypt the data because the key that you used is not on it. We encrypt the software, the full manifest, and the data, and we sign everything as well. So we hash it and sign it. And so when you receive your snowball, it's a brick until you give it your key, which is stored on the cloud, or you can download it, say, to your laptop. Once you give it your key, then the first thing it will do is it will go through and attest all of its software to make sure none of it's changed, and all of its data to make sure none of it's changed. And then it'll go through, check all its anti-tamper, make sure that's all okay. And then once it's finished with all that stuff, it'll go through and start using your key to decrypt the boot, and then it'll boot up, right? And then you can start using it. And while you're using it, it's actively using its 2 keys. And your key, as soon as you turn it off, your key's destroyed, and so your data's secure on here.
So how much does one of those cost?
It's $6.
$6. And what kind of computing power does it have?
So this is $6 a day. It's a use for the cloud, right? And so generally, because people will use it for a period of time. So for the snow cone, it is 2 x86 cores on EC2. I think it's around 8 gigs of RAM and 8 terabytes of storage and 10 gig networking.
So it's like 100 megaflops or something on that order.
I don't know. It's not that much, right? But for the snowball, the compute optimized has 5,300 GPUs and 52 x86 cores. That's $30 a day to use. 100 gig networking, 100 terabytes of storage, 8 terabytes of NVMe flash, and all of them are ruggedized. All of them have the triple encryption and all those other things. So
if I were in the middle of the Sahara Desert, you could fly over with a C-130 and airdrop me one of those. And
with a parachute. Yeah.
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 That's cool. I had no idea you guys had that kind of stuff.
Yeah, it's interesting. This was the way we designed this. Remember, I did the robots in the ocean where they have to handle about 300 Gs in a hurricane, and so I learned a lot about how to design hardware to handle that, and we put all that into the way this is designed. So And so it's got all of the impact absorption and things like that capabilities for it. And so the Snowball is under 50 pounds for all common carrier, and you can check it as luggage without paying a fee. It's rack mountable, and it's also Transcom rated for top secret shipment as well, and secret shipment rated, and integrated with their logistics with the E label. And so 50 pounds is a requirement for that. This is under 5 pounds. And the reason it's under 5 pounds is it's designed for drone operation. So there's a large number of drones that can carry 5 pounds around, more for photogrammetry and aerial surveys and other things like that. So you just hook it up right there, and there you go. And it's also got Wi-Fi and Bluetooth, and it's got USB-C ports. And these are two 10 gig ports with a switch in it. So there's a lot of cool use cases for it, but it's really for us, it's about collecting data on the edge, processing on the edge, and then being able to ship it back to the cloud. I mean, if you tried to upload this 8 terabytes on your Comcast network, it would take a long time, right? To upload that. But as more and more network becomes available, I think the issue is you just always have more data collected at the edge and more things people want to do at the edge. So like the movie studios use Snowballs for shooting movies. The movies today are shot in 4K and 8K, but they're working on a 12K, right? And so, it just gets bigger and bigger and bigger, and it's harder and harder. As much as, we have this Kuiper satellite system we're working on, which will be 3,200 satellites that'll offer 1 gigabit per second with 30 milliseconds latency pretty much all over the world. That still isn't going to be enough for a 12K movie stream, while they shoot their raw footage, right? So there's always going to be this, or seismic data or a lot of other things that happen at the edge. So I think there'll always be some need. I'd love to not have to make those and have enough pervasive networking everywhere where you could just send it right into the cloud, right? But there's reality and physics and other things like that we have to deal with in our whole infrastructure. So.
Well,
Oh,
you
Bill, it looks
covered
like
a lot, Bill. Go ahead, Christy.
it looks like there's a question in the chat from one of
Sure.
our students, and it's Stephen, and he asks, is it running in some version of RAID, or is there some other built-in redundancy?
It is rated. Yes, that is correct. It's RAID 5. Yeah, when they're clustered, they actually use a Reed-Solomon distribution across multiple of them. So it stripes the data across multiple of the storage devices. So you can lose multiple devices and still not lose your data. On the individual device, it's rated. Yeah, so for example, this is 8 terabytes of storage that you have access to, but it's actually about 10.5 terabytes raw. And the reason that you have 8 is that it's rated. So there's redundancy built in.
I can see huge applications for construction and civil engineering, also environmental monitoring with all these sensors and the way you've got all this data coming in and pipelining it and streamlining it. And then, like I said, the robotics. You've got a lot of stuff with robotics that I never appreciated.
Yeah.
And Vince and I were actually where Vince had a good idea for automatic, because we have to inspect our reactor fuel every other year, and it's a real pain to do manually, and we need a robot that does it. And so we're trying to look into options for that. So maybe we need to look at what you got for robotics and try to team up with that. That's pretty cool.
Yeah, that would be interesting. It's again, so we don't build the hardware, we build the software for it, right? And the simulation and test. So we would build a 3D model of your reactor or wherever it is you're going to be testing, and you could train your robot to do the inspection without ever sending it in there. And
that's really cool.
Yeah, that's what's cool about it. Like you could like train a robot to water plants it's never seen, for example, by doing a simulation.
So if we wanted to do that, do we go to the AWS website and go through, and how do we?
Yeah, it's called RoboMaker. You can go take a look at it, and you can pick your robotics model. And there are a bunch of different 3D models already out there you can download, or we can help you build one.
Okay, we may need to look into that, because that's a problem we're trying to solve, and it
Yeah.
looks really cool, and it looks like you got the tools there, so,
Again, it's a lot of Lego bricks, so you got to put it together.
yeah.
We continue
Well,
to,
that's the secret sauce, right?
I know we kind of continue to move up stack though for things like, I mean, like World Forge, where you generate these synthetic interior spaces. We have like recognition, so you can stream the data directly into recognition. It can recognize objects for you without you really writing any code. That's all built in. All the alarming and metrics are built in, but what you want your robot to do and what's unique about your robot is up to you.
That's really cool.
Well, we're coming up on 20 minutes past the hour, which is the time that is allocated for class. And I want to be respectful of the students' time. I'm so thankful, Bill, that you were able to join us today and give us a presentation. And it's going to be really nice for our sophomores to be able to hear about this information from your presentation today as well. So I just want to thank you for joining us, and I want to allow the students to dismiss themselves. And Glenn and Bill, if you'd like to stay on, you're welcome to use the channel to visit as long as you like.
Okay. All right. Yeah, we'll do that. And, it'll be interesting. You'll record it. You can go watch it, 10 years from now and say how right or wrong I was.
Yeah, exactly. We'll archive it and pull it up in the future. And
Wow, great talk. Very interesting.
the recording now so that you can have whatever private conversation you want after.
Okay. All right.